I'm going to show you how to do calculations for an unnamed thermodynamic process. So most of the time when you're doing calculations for thermodynamic processes, you can identify the process by name: adiabatic, isothermal, isobaric, isochoric, and there's special case formulas associated with those. But what happens if you're confronted with a situation where the process is none of those named processes? Well, you can still deal with it. Provided you have enough information, it is possible to do all the calculations you would normally do for a named process. So I'm just going to make one up here, and it looks like this. Of course, put the information in the form of a PV diagram because that's useful from the point of view of work. We can look at that geometrically. So we put pressure in pascals on the vertical axis. We put volume in cubic meters, SI units of cubic meters on the horizontal axis, and I'll just give you some data. So we're going to start with a pressure of 1.2 times 10 to the 5th pascals, and we're going to start with a volume of 0.002 cubic meters. Okay. And we're going to double both of them, and it's going to be a straight line in the PV diagram. So we'll double our volume to 0.004. We're going to double our pressure to 2.4 times 10 to the 5th pascals. And like I said, it's going to be a straight line. Okay, that's going to be helpful because we'll be able to use geometric method to determine the work. Okay, so we need at least one more thing, and we'll state that the initial temperature is 250 Kelvin. Okay, so we know initial pressure, volume, and temperature. We know final pressure and volume, and that's enough to calculate all the states. So it's a good idea to calculate all your states first and then go on to calculating the energies. Okay, so let's think about the ideal gas law, PV equals nRT, and I'm not going to rearrange this for temperature. I'm just going to think about this in terms of proportions. So if I'm doubling the pressure and doubling the volume, and we normally hold the number of moles constant, and the ideal gas constant is constant. So what would happen to the temperature? You might pause the video and think about that and see if you can calculate that in your head. But what it'll be is 4 times. We double pressure, double volume, we're going to end up with 4 times the temperature. So we end up with the temperature up here would be 1,000 Kelvin. That's pretty hot. Okay. So let's last thing we want to do is calculate the number of moles. So we solve the ideal gas law for number of moles. So we have PV over RT, and so and we can do this for initial or final, doesn't matter. We should get the same answer. So pressure, we'll just do the initial. So initial pressure 1.2 times 10 to the 5th pascals. Okay, I'm going to throw in SI units here, so I'll get SI units of moles for N. Volume of 0.002, R of 8.3, forgot my division sign there, 8.31, and a temperature of 250, and I end up with N equal to 0.1155 moles. Okay, so I've got my states completely defined. Got initial pressure, volume, and temperature, final volume, pressure, volume, and temperature. I've got number of moles. Now I'm set up for success to calculate the energies. So, and you can usually do this in any order. In this particular case, though, heat will have to go last because there's not a general purpose formula for heat, but there are general purpose methods for change in thermal energy, and there are general purpose methods for calculating the work. So we'll do it in that order. So change in thermal energy is equal to N times molar heat capacity at constant volume. And that may seem weird that we're including such a variable in a process that's not constant volume, but for reasons that I don't want to get into now, I assure you that this is correct. Okay, so number of moles, molar heat capacity at constant volume times the change in temperature. Okay, so, oh, I didn't give you the type of gas. So this number will vary depending on the type of gas. So let's assume that we'll use a diatomic process, or diatomic gas. So the change in thermal energy will be number of moles, which you calculate to be 0.1155. Molar heat capacity at constant volume is 5/2 R for a diatomic gas. Be 3/2 R for monatomic. And of course, if you knew the exact molecular composition, you could do even better than that. So this is just a best guess for an unknown diatomic gas. Okay, and then the change in temperature would be final minus initial, 1,000 minus 250. We can do that in our head and just write down 750. The temperature went up by 750. And so we get a change in thermal energy for this particular gas of 1,800 joules. Okay, so it gained energy. The molecules are moving faster than they used to, and rotating faster than they used to. It's diatomic. Okay, so what's next? So now we can calculate work by looking at the area under this line. So it could be a calculus problem if it was a curve, or if it's a straight line, which it is here, then we can just do the area of this rectangle plus the area of that triangle. And then we do need to think about signs. So an expansion for a gas, it's giving up energy to the environment. So we have to manually put in a minus sign. Of course, if you're doing integral, that sign would take care of itself. But since we're doing geometry, you do need to manually put in a minus sign. So work will just be minus, and I will say rectangle plus triangle, okay, or area of those things. And so then we just need to use a little bit of geometry to think about the areas of the rectangle and the triangle. So minus, okay, the base of this rectangle would be 0.004 minus 0.002. So 0.002 times its height, which is 1.2 times 10 to the 5th pascals, plus, okay, well, 1/2 base times height. So the base is the same, this width, 0.002, times its height, which is, happens to be 1.2 times 10 to the 5th. Okay, so a lot of these numbers look the same, and that's just a coincidence here. But I wanted to make the math easy for myself. Okay, so we throw those numbers in our calculator, and we get an answer of minus 360 joules. Okay, so what happened here is that this gas gained 1,800 joules in total, a net 1,800 joules. It lost 360, so where'd that energy come from? Well, it had to come from heat input. So we can think about this in terms of the first law. The change in thermal energy can be attributed to heat plus work, and then we can calculate heat would be change in thermal energy minus work, and we throw in the numbers, 1,800 minus negative 360. So we had to have 2,160 joules of heat input in order to have output of 360 joules of work and get a net gain of 1,800 joules of thermal energy. Okay, so that's an example of how to calculate states for an unnamed process, very similar to what you would do for a named process, but then for the energies, the calculations do look a little different. So that's what's special here. Okay, so hopefully you can now be confronted with an unnamed process and perhaps do these types of calculations as well. Okay, so have a good day. I'll see you next time.